Okay, well, let's get started. Hello, everybody. Welcome to today's webinar. My name is Peter Blazer. I'm going to serve as your host. And in a moment, I'm going to introduce our primary speaker, Dr. Shashank Kara. Today's webinar is the second in our Barracuda application model webinar series, and we'll be discussing proppant transport and hydraulic fractures. Please note this webinar is being recorded. The playback will be available soon. You can find all our webinars on our website. If you click on the resources button, and it'll bring a sub-menu with webinars presentations, and that's where you'll find this and others. Should be up within the next 24 hours or so. One thing that would be helpful for everybody is if you have a question, other people are probably thinking about it too, or could spawn other discussions. So questions are highly encouraged. There is a questions tab there, panel. If you enter a question for the staff there, go ahead and enter those as you think of them. No need to wait to the end. We have allocated a significant amount of time for questions at the end of this webinar. So please ask those as you think of them. First, a few introductory points here. Some of you are new to us, some of you existing customers. So for those that are new, here at CPFD Software, we are advancing multi-phase simulation and technology specifically for fluid particle systems. Now, in a lot of cases, those are fluidized beds, fluidized bed reactors. Today, we're going to see a different application, so in liquid particle systems. Regardless of the application, our product, our primary software product, is Barracuda Virtual Reactor. Virtual Reactor models the three-dimensional transient hydrodynamics, that's the multi-phase gas particle or liquid particle flow, the heat transfer, the thermal calculations, and also can be coupled with chemical reactions at large scale, at full industrial scale. And it's used to improve performance and reliability through simulation. For existing units, that could be determining the root cause of phenomena, often underperformance, reducing risk of changes through virtual testing, and identifying additional optimization opportunities. And for those of you that are developing new technology, bringing it to the market, it's used to broaden the research, test broad ideas, and then more quickly and at lower risk go through that commercialization and scale-up process. And interestingly enough, the objective basis of the software is often used to communicate the unique technological merits of your technology to all stakeholders, be those customers or partners, investors, and so forth. The product, the software, Barracuda Virtual Reactor, it is physics-based engineering software. It's CFD plus particles. In fact, it's the only one commercial package focused specifically on large industrial scale and with the ability to go on to chemically reacting flows. It's a full software package, everything from pre-processing, grid generation, solver to post-processing, and it's broadly deployed. It could be on premise or on the cloud, Windows and Linux operating systems, and we are parallelized using NVIDIA GPU and multi-GPU technology. And there's really two types of systems that the software is used to model. The first is gas phase domains with particles. So this is our traditional application here of fluidized bed reactors. For gas phase systems, the fluid is gas, so it's compressible. There's no limits in the number of materials, and the gas for discrete phases, be those particles or droplets. No limits in the number of species of particles or droplets, full particle size distribution, all coupled with that heat transfer and chemical reactions. And just a few years ago, we added a complementary technology there where instead of a gas phase domain, now we have liquid phase domains, and with the discrete phases of particles or bubbles. And so the same sort of no limits to the number of materials and species and full size distribution, again, coupled with heat transfer and liquid phase reactions now. And with that, one last slide, and I'll hand it over to our presenter. This is a webinar series on application models, and I think it would be helpful to just take a brief moment and say, what is an application model? So application models are sample cases that we've set up for specific applications. So these are on our website there under the resources tab under application models. There's 10 of them there. We continue to add new ones. We're continuing to promote them here on this webinar series. These are models that are taken somewhere from the public domain. So we'll have references to the literature for where this information came from. What's the geometry? What are the process conditions? If it's a reacting system, what are the reactions and rates? We show sample results. Then we show you how you can do it. So how would you set up in post-processing? Those instructions are included in the application models, and Shashank will show that in a moment. And these can be downloaded, run, and customized by the user community. So this is the second one in the webinar series. And the prior one is available on our website. This one will be there too, and we have a few more scheduled that I'll tell you about at the end. And without more ado, I'd like to introduce our speaker. Our speaker is going to be Dr. Shashank Kara. Shashank has 20 years experience in thermal fluid sciences and CFD. His PhD is from Oregon State University. He has broad experience at commercial companies and national labs, universities, including Baker Hughes, ANSYS, Pacific Northwest National Labs. His background includes multi-phase flows in things like pipes, wellbores, porous structures, other heavy oil applications, and we've been really privileged to have him with us since 2023. So Shashank, with that, I'm going to turn this over to you.
All right, yeah, thanks a lot, Peter. Can you see my screen and can you hear me all right?
Yes, on both accounts.
Okay, perfect. All right, yeah, firstly, I just want to take a moment here and thank everybody for taking the time to join this call today. I know we have people joining all over from the world today. So again, without any further ado and delay, let me jump straight into the topic down here. What I'm going to talk about is proppant transport in hydraulic fractures and how one can use Barracuda to look at this particular problem. A quick agenda for today's talk here. I'm just going to start with a couple of slides, just introducing generally what hydraulic fracturing is all about for some of you who are not familiar with that. And then we'll specifically look at how Barracuda solution applies for proppant transport problem and how it differentiates itself from some of the other solutions out there. Then we'll actually look at the actual proppant transport application model that we have on our website that Peter was pointing out to. And then before I actually go and demo and show you, the setup itself within Barracuda, I want to actually take some time and show some results from field scale multi-fractures that we've also run. So Barracuda can, not necessarily be used only for small scale domains, but actually real world geometries, real world problems, and how it can be used to solve some of those. So after I touch on that, I'm going to then jump into the demo section of today's talk. With that, hydraulic fracturing, I think it's best explained through this picture down here. So generally, this is what I'm showing down here is it's sort of an oil drilling rig. You basically have a pay zone where you want to sort of identify your hydrocarbons. You want to extract that. So you basically drill a well, go vertically into your pay zone, and then essentially go horizontally. This is a single well down here. And what happens is generally with a formation like shale, the pores are not interconnected. So the oil is not going to freely move, oil or gas is not going to freely move through those pores into the wellbore. And you have to actually connect those pathways. To do that, what is essentially done is this fracking process in which you're injecting high speed, high pressure fluid. And this fluid is not just your regular water, it's usually mixed with some sort of polymer to increase its viscosity, and then also make it basically shear thinning fluid. So once you sort of pump it down, and then you sort of create some perforations through a perforating gun into the casing and the formation, this high pressure water essentially fractures and creates these fractures in the formation. So once you actually create those fractures, that's when the next step becomes important. So the fractures are created now, but these fractures would close if nothing is holding them apart because of all the earth and this soil present above it. And so what you do is, as soon as you fracture them, you then inject this slurry mixed with proppants. So you have the same sick water, and now you're injecting, the proppants could be simple sand, or this could be highly specialized solid particles. The idea is these proppants then go and settle down in these fractures and keep them propped open, essentially, right? So once it keeps open, the proppants settle down, you create sort of these semi-permeable pathways for the oil to flow, and then you extract it out. Now, the economic impact of this is significant. Like it is estimated that anywhere between 75% wells for natural gas in the US and about 48% of production wells in the US right now are done using hydraulic fracturing. It's a multi-billion-dollar industry globally. So any optimization that can be done in the process is significant savings in terms of dollar amounts. And so one big optimization that can be done, as you can imagine, is how are these proppants actually placed inside these fractures. You ideally want these fractures to these proppants to travel as far as possible in each one of these fractures, and also essentially, if possible, fill all these fractures uniformly, right? So you can maximize returns from your pay zone. And this is where a tool like CFD actually plays a role, because it's almost impossible to visualize what's happening downhole. And so using CFD models, you're solving your first principles governing equations down here. So you can then essentially sort of visualize where these proppants are settling down, how they're moving, the complex interaction between the liquid and the solid. And then you can think about optimization strategies. That said, I'm going to narrow down my focus and then focus on what Barracuda virtual reactor solution is for Proppant Transport. And this is where I think Barracuda truly differentiates itself, because from the ground up, Barracuda is built to be a multi-phase flow solver. So we're not like other conventional solvers which started off as single-phase solvers and then added the multi-phase capability on top of it. So the core technology itself is built to handle both liquid or gas, and then your solids. These could be droplets and bubbles as well, right? So the architecture is fundamentally built up from the ground or based on that. We use a methodology called MPPIC methodology, and what this allows us to do is basically allows us to solve this complex physics, which this Proppant Transport is, right? I mean, you basically have a four-way coupling between the solid and the particles, between the fluid and the particles. The fluid is dragging the particles, and then it experiences a force back on it. You have particle-particle contact interactions going on. You have particle-particle frictional interactions going on once the bed settles down. And then you also have the particle and the fracture walls interacting with each other. So all of this phenomena is happening simultaneously, and you want your code to be actually able to capture that, which is what Barracuda is built up to do, and it does that. And then the other big piece of this thing is it's fair enough that you can actually do this, but you want to be able to do this on real world geometries or field scale problems. And that's where the scalability of Barracuda comes to the fore. So we are one of the first few early adopters of GPU technology. So our solvers, again, take advantage of all, the parallel processing capability of GPUs. And so very routinely, we are actually solving tens of millions of computational particles, and we have that capability to include this in large scale domains as well. And that is actually, because of the combination of our architecture as well as the GPU acceleration that we provide. With that said, obviously, the value proposition down here from such simulations is, first you can visualize what's happening down there. Once you visualize what's happening, you can look at how the distribution's looking like, whether it's more heel dominant or, and then if that's the case, what can you do essentially in terms of operational changes to mitigate some of those? And we'll briefly touch upon that in these multi-fractures results that I have. And then obviously you can also look at solving certain problems, right? So once you have a well-validated CFD model, you start looking at the behavior of the fluid and the slurry downstream. You can start identifying problems essentially, and then think about mitigating those. And then last but not the least, the idea is once you start building multiple of these simulations, you can then think about building a reduced order model on top of it, which acts as a digital twin essentially, and then you can start getting some real-time answers as you're actually undergoing this process here. With that, I'm going to jump into the actual application model for today. As Peter was pointing out, generally these application models are based on some publicly available literature. So in this case, we happen to actually take the geometry from this experimental work of Mao down here. So this is a 4 feet by 1 feet fracture. There are 3 inlets to the right down here, and there are a couple of outlets on the left here. We're injecting slick water at 6 gallons per minute, 1 centipoise viscosity, and then the proppant concentration is 1.7 ppg. Importantly, we are using a 40 by 70 mesh size for the proppant down here. This distribution was not provided in the literature that we actually took this geometry from, so this is something we assumed. 40 by 70 is a very commonly used mesh size. The key point, though, is that Barracuda actually allows us, the MPPIC methodology allows us to actually include the full PSD. So we don't have to assume a mean diameter down here, or we just run multiple simulations at different diameters. We can actually include the full PSD, and that's what I'm showing down here. It's the Proppant diameter and the cumulative mass distribution of that. And then the other key point is just the liquid itself. As I was mentioning, this is water mixed with some sort of polymer. So this acts as a non-Newtonian fluid, and therefore the shear stress is not linearly proportional to your strain rate. So to account for that, we actually use a power law model. Generally, for shear thinning fluids, n is less than 1, and we use this define this as a user-defined RAG model inside a setup. And I'll touch upon that when I actually open up the software and show you where it is. But and we do provide some instructions for this, or some description for this on our website as well, which I'll highlight. Okay, so what I've got going down here is an animation. There are 3 separate videos that are playing down here. The first one is actually showing you the proppants coming in, and we're coloring these solid particles by their volume fraction. So you can see basically the slurry coming in, it's settling down due to gravity, and it's forming this proppant mound, a bed, essentially. In the second video, I'm actually coloring these by velocity. So they do come in with a certain velocity, but once they settle down, they're pretty much stationary and not moving towards the bottom down here. And then the last video is actually showing you the age of the proppant itself. So the proppant that has come in initially is all colored in red because this is close to 40 seconds age, right? So just a brief overview on the type of results that one can start looking at once you have run some of these simulations. We can also quantify some of this data, and that's what I've got down here. What we're plotting down here is basically the proppant bed height. This would be sort of tracking the height of the proppant bed there. And we're doing this at different times. So we're doing it at 10, 20, and 40 seconds. The lines are from the CFD simulation, and the symbols are from the experiment down here. The first thing to notice is that there's a great qualitative match between both the CFD and the experiment, right? So initially the bed starts off flat. With time, you start building up this mound, and then you have this sloping structure towards the end down there. However, there are definitely differences between the bed heights between the CFD and the experiment, and this is primarily attributed to the unknown proppant PSD. As I was mentioning on the previous slide, we assumed a 40 by 70 mesh in this case. To verify that, what we actually did do is we ran a couple of other simulations. So we took like the smallest proppant size and the largest proppant size, and so those are actually colored here in pink and green. And so when we run those simulations, we do see that at the 40-second mark, right, there's a big variation here. So the size distribution of the particles plays a significant role in how the bed essentially settles down, the height it reaches, and the spread itself. So provided one does have the actual PSD, one can use Barracuda actually to make good predictions for the formation of the bed here. With that, before I jump into the demo for this model, like I said, I want to actually show some other results where we have these, I've set up some field scale multiple fracture simulations. And the idea is, again, once fair enough, you take your model, like the Proppant Transport application I was showing, you validate your model, you come up with the best possible settings that you want to use, and then can you take this and then subsequently use for field scaled problems, right? And that's what we're trying to do here. In this particular example, I've got actually three fractures essentially, and I'm playing with a couple of parameters. One parameter that I'm playing around is with the fracture spacing. So how far away are these fractures from each other? And this is to account for what is known as this stress shadow effect. Essentially, I'll talk about that in a second. The other thing is these fractures are realistic, so they're not just straight out wedges. You have tapered geometries, so they start off wide near the elbow and then they taper off. And lastly, we'll also look at a couple of pumping flow rates. So we'll look at 30 barrels per minute and then 45 barrels per minute, and then we'll compare some results again across these cases. Okay, so the first thing I've got here is this multi-fracture domain. As I said, there are three fractures in down here. the proppant is injected into the wellbore from the top of the screen down here. This end is actually closed. So once the proppant gets in, it then essentially it wicks down into these fractures. The first thing one notices is that these are real world geometries, right? So you have hundreds of feet of length of these fractures. The spacing between these fractures is right now 5 meters. And the obvious thing one notices is that the lengths of these fractures are not the same, right? And this is what I was referring to, a phenomena known as the stress shadow effect. So what happens is basically, when the first fracture is actually forming, you're injecting this high pressure fluid, the first fracture is forming, it essentially creates or squeezes the rock around surrounding that regions, right? So the first fracture opens up, but it creates this extra pressure or what is known as the shadow effect on the surrounding rock. And therefore, the fracture that is immediately next to this, is not as well developed, essentially. And so it is actually stunted in length. If you can see, the first fracture is 60 meters, whereas the second fracture is only 15 meters in length, because it experiences this stress shadow effect significantly. This third fracture also experiences this, but also on a lesser extent. So it only grows about 35 meters, right? So this is quite typical of what we see in real world, and that's what we create our geometries based on. The other set is now basically okay. The other one is for 10 meter spacing down here. So you will see that the spacing is bigger between them, but then because now there's less of a stress shadow effect, the third fracture goes to 45 meters, whereas the middle fracture still experiences that, right? So it's not as long as the first fracture. However, when we move to the 20 meter spacing down there, both the first and the third fracture lengths are almost the same, and the second fracture is almost 50 meters in length down here. The other important point to note is, as I was mentioning, all these fractures start off at 1 inch width down here, and then they taper off, right? They taper off to 0.6 and 0.4 inches. Again, this tapering off is also some function of your stress shadow effect. So, again, realistic geometries down here, accounting for stress shadow effect, and we want to study what happens when we have these fractures spaced in with multiple spacings here. Okay. Firstly, as I said, we are using 2 pumping flow rates, 30 barrels per minute, 45 barrels per minute. The well toe end is closed. The proppant and the fluid are allowed to leave the fracture toe ends essentially. We are using a 40 by 70 mesh sand here. Again, we define the full PSD available. And most importantly down here, we actually run these simulations, which are hundreds of feet in length, and we're actually able to simulate about 20 minutes of physical pumping time down here. And we can do this, within about 16, 17 hours, roughly, for all these cases, right? And then to do this, we only use 1 GPU card, which is our RTX 6000 on a data center. And so this is actually quite significant, because this is where truly the fundamental multi-phase architecture of Barracuda, coupled with its GPU acceleration, comes to the fore. Is you're actually able to solve some of these real-world geometries, and real-world physical pumping times. You're not looking at times of seconds down here. You can do 20 minutes, you can do 60 minutes, and you can solve them on a single GPU card on your workstation, essentially within a matter of less than a day or a couple of days, essentially. So that is quite powerful. The insights that one gets from being able to turn around these things so quickly is actually quite important. With that said, I'm going to play a video down here. I've got these different spacings lined up, and I'm actually going to show you how the proppant actually transports and settles down in these fractures. So essentially, you see the flow coming in through the wellbore. It's starting to enter these fractures here, and then with time, you can see this is the time playing down here. At time, you see the bed actually starting building up. The slurry on the top still continues to go, but you see settlement of particles happening. One thing to notice is the third or the toe fracture, right? As you increase the spacing and you go to 20 meters, none of the proppant actually reaches sort of the third fracture down there. So that is, again, something interesting to look at. And so what we can do is we can try to quantify some of these results, which I'll try to do here shortly. I just want to make sure that the animation plays once more. So, again, I've accelerated this animation quite a bit, but we are playing this till about 1200 seconds down here. Okay. All right. With that said, these are the same 3 fractures. I've taken snapshots of them at 1200 seconds here, or 20-minute mark. And then I'm basically going to actually show you, quantify some of this mass distribution. So what I've got in this plot is a bar graph down here. The fractures are 1, 2, and 3. So this would be your heel, the middle, and the toe fracture. Each one of the color represents a certain spacing. So the blue is for 5 meters, the orange is for 10 meters, and the green is for the 20-meter setting. The first thing one notices is that in all three spacings, the first fracture gets most of the proppant mass compared to the other two fractures. However, the results are a bit more nuanced than that. What you see is basically for the as you increase the spacing, the first fracture actually cannibalizes most of the proppant mass into it, and then for at least for and then that trend continues actually. So what's happening down here is basically when you have this tight spacing with 5 meters, because of this stress shadow effect I was talking about, you get a back pressure on the first fracture, and that actually forces more fluid to go into a second fracture. However, when you increase the spacing, basically, right, and let's say you go to 20 meters, pipe friction starts dominating. So basically, the fluid loses momentum and the particle starts to settle down. So most of the proppant ends up in the first fracture. Some of it goes into the second, and actually, in all three cases, the toe fracture is pretty stark if you actually quantify the mass of proppant that is going into them. Okay, so can we actually mitigate this or sort of change some of this behavior if we increase the pumping rate, which is what we try to do in this particular case. Again, I'm showing the 10-meter spacing case down here. This is 30 barrels per minute and 45 barrels per minute. Again, I have a video playing down here. So visually as well, we can see that more proppant is actually getting into the third fracture for the 45 case compared to the 30 case. And we can quantify this as well, right? The same way we've quantified it for the other case. Again, 3 fractures. And what we see is as we increase the flow rate, essentially, we are taking some of that mass that was entering the first fracture and putting that into the second one. So basically what happens is with the increased flow rate, there's higher inertia. So, the particles and then, get carried past the first fracture, and then they can make it into the second fracture. Whereas this is not what quite we see at a lower pumping rate. Again, but even with this increased sort of pumping rate, the third fracture still doesn't receive, in terms of absolute percentage of mass, that significant amount of proppant here. Okay, so again, just to give a flavor of the kind of results one can start looking at once this domain is set up, and it's just a matter of hours to get these results here. With that said, I just want to show one last set of results that once we have all the information available from Barracuda, where it gives us this proppant volume fraction, the mass distribution, the PSD, one can then take and start looking at some interesting variables that people actually out there, working in the oil and gas industry care about. One of those parameters is this propped fracture width. And as the name suggests, essentially, right, once you have this proppant settle down, you stop pumping, you actually want to see what's the width of the fracture that is going to stay propped open, such that, that is where you actually are going to produce oil from. And it's one way to define it is, this propped width is a function of the initial width and the volume fraction divided by the close back volume fraction, right? And once we have this propped width, we can actually define another quantity called, or calculate another quantity called fracture conductivity. So, proppant settles down, you calculate what the propped width is. If you know what the permeability of that bed is, based on, and again, because this is the full PSD down here, so if you can account for that, permeability of the settled bed down here, you can then calculate the total flow capacity from each fracture using the conductivity down here. So which is what we do. And this K value is permeability. I'm using the Kozeny-Kármán permeability relation down here. Phi stands for porosity, S is the surface area of each proppant particle, C is a constant. So if I do some post-processing on some of the data that I get from Barracuda, I can start getting plots like this. So what I'm showing down here is for the 10-meter case, the first fracture and the second fracture. And this image here is propped width in terms of images. So you can see that the propped width is much more wider, closer to where the well bore is, and it goes down as you move further away from it. Same thing with the conductivity as well. So you're going to conduct more oil where this is all dark and red, and the units here are millidarcy feet for the conductivity. Same thing again for the second fracture, right? So just because the proppant settles down and you see it moving, or just because the proppant enters the formation or the fracture down here, it's not good enough. You want to see where it's settled down, essentially, and then you can start estimating some of these parameters based on that. Okay, with that said, I am now going to transition into my demo. All right, so let me pull up my website that Peter was showing earlier here. So this is our CPFD software website. You go to under resources, you would go to these application models. And we've got a list of all these application models here. The one we're going to look at today is this Proppant Transport and hydraulic fractures. Click open on that. And what you see is generally, the first thing you'll see is a general overview of what this post is all about. And this is publicly available. You can click on this access model. Again, this is available on our public site. You don't have to be a registered website to read through all of this post. Only to download files is when you will actually have to be a registered user. But one can actually open this up on our website and actually start looking at this post, right? So generally the format is we start off with a broad high-level introduction on the problem itself and what the importance of solving this problem using CFD. We then briefly show the model definition. We list out the literature sources from where we have gotten these models from. And then and this varies in each application model. In this particular application model, defining this user-defined non-Newtonian drag model is a significant input, and therefore we spend time actually explaining what this is all about. And then we show a screenshot of how that implementation actually looks like. If you look at some of our other posts where for example, reactions and kinetics are important, that's what we'll spend time on. We'll explain basically where the reactions are, what they're doing, where we've gotten this kinetics from, and so on. And then once we do that, we actually list out a few of these results. I've already showed you some of these, the animation. We try to validate whenever we can. We try to validate our models. And once we do that, here's where you get to the interesting stuff, right? So when under post-processing, you'll find this hot link for support file. If you click on this, and if you're logged into our website, it takes you to this page here. So here's where you actually get the zipped up folder, including the setup for this model. I click on that. By default, it goes into my download folder. And then what happens is basically, let me bring that up down here. Go into downloads, and you can see that this is the zipped folder down here. I've already got it unzipped. So let me just go into that model down here for a second. If I go in down here, you actually see the project file we have. We have some of the zip files which define the boundary condition, and we also have an STL file for the geometry. Now, all of this is provided to you as a user to use it. Let me double click and open up the window down here. Okay, maximize this. Okay, so first thing, if we go down here, you will see that we do have the geometry imported in. We have created a grid. In this case, we can create a nice structured grid down here. Go to global settings. We have defined the gravity direction that happens to be along the z-axis in this case. And then under base materials, we have got both our water, slick water, as well as our sand definition. So if you go down here, you see this is where the viscosity is defined 1 centipoise. And then if you go to frac sand, we can define the density for the sand down here. All right, so set up down here, and then here's where you would actually set up all this particle and particle liquid interactions down here. So we set up how these particles interact with the walls, how much momentum they retain when they hit each other, and when they hit the walls, and so on. So all of that setup is already done for you here. And the interesting part is this drag model. So we have a list of all our drag models which are predefined, but in this particular case, as I said, we're using this user-defined drag model. So this is where you would come in and actually add a new user-defined drag model, and you define it. Now, you can look at the post to see some details about how this is actually implemented. We have further details for user-defined drag model definition, or how to do that also in the help guide. So I'd strongly encourage you to look through that. Once you do that, and then you define your particle species, which is essentially your frac sand down here, and I've defined my full PSD, as you can see here, right? Define the frac sand with its full PSD, and then you come in here, you define your flow conditions. In this case, it happens to be, like I said, we have 3 inlets essentially that we define our flow inlets from. And then we have a couple of pressure outlets down here. So once that's done, that's pretty much what you need to do in this case. It's all set up for you. You would come down here to run option. The first thing that you want to do is actually generate the grid. We usually don't generate the grid because for some of the bigger domains, that can actually take up quite a bit of memory in the zipped file, and we want to keep these zipped files as small as possible in terms of sizes. So once all you have to do is go back to setup grid, generate the grid, come to run, and by default, I've got one single GPU in my laptop down here, so I've got that turned on. If you don't have that, you can check this option off, and you can use CPUs if you have them. All right, so with that said, all I'm going to do is I'm going to say run solver. Let me bring over this window here. And I'm going to do this. Like I said, I have only one GPU, so I'm going to use the same GPU ID. And boom, it's already set up for you to run, right? Well, that's all. So basically, open up this GUI, compare this with what's written out there in the post to understand some of the key features in this post. And then once you do it, you can then start running these. And if you want to then start making modifications to this post, right? If you want to put in your own SAN PSD, if you want to do the own, a different sized domain that you want to bring in and regulated, all of that can be done using this existing setup. I'm not going to run this simulation, so I've stopped it, but I've already run this and I've got that open down here. So once you run it, and then you go down to post run down here and you say view results, that actually brings up our tech plot window. The first thing that I'm plotting down here is this particle volume fraction at the 40-second mark. Now I can start looking at things like particle size distribution. I can look at particle speed. I can look at particle residence time and so on. So all of this is actually available to you once you start running the simulation. And so once, the other portion with that is you can also subsequently use Python to read off some of these values from techplot and do further post-processing. But that is something that we do not have time today to cover. So with that, I'm going to turn this back to Peter.
Thank you, Shashank. I'm going to take over a presentation and go over a few slides here. In the meantime, anybody who has not yet put in their questions, please do so. We're going to get to that in just a few moments. So a few housekeeping things before we move on. I should let everybody know that Barracuda Virtual Reactor is available there's a few different ways you can engage with us in the software. The first is software licensing. That is using Virtual Reactor in-house. We have single site and everything up to global enterprise licensing available. The software can be deployed on-premise or cloud served. We also have a services team that can work on specific projects with you. And I particularly want to highlight one of our training tech transfer options called Quick Start. So we obviously have new user training. There's a class going on this week and more coming up. Great way to try the software. But Quick Start does exactly what the name implies. We know our software fairly well. So with Quick Start, we set up your first model or models. Then we hand that over, train you in their use on your own system, and provide the software licensing where you continue to run thereafter. And so that's something that we have available. And we do partner with a variety of organizations on R&D, whether that be fluidization, on the models themselves, technology, machine learning, reduced order modeling, AI, and so forth. So it's a few ways to engage with us. Next, there are a couple ways to work with us in person or web-based. So first of all, in person, these are all primarily in the first quarter with one exception. So in person, if you're in Houston area, PSRI, a good partner organization of ours, does a fluidization training seminar. They have one coming up in Houston in February. We're going to get a guest lecture there. But that's a fantastic training for anybody working with gas particle processes. We'll be at the SPE, the Society of Petroleum Engineers, Gulf Coast section, CFD group annual meeting is coming up in March, also in Houston. And a couple opportunities in Korea coming up in the first quarter, a PSRI seminar, and then a workshop on emerging fluidization applications coming up March 16th through 20th. This is not the first quarter, but I also want to point out the Barracuda Virtual Reactor Users Conference. So we do this every 2 years nominally, and it's coming up in June next 24th to 26th of 2026. So please join us there. Save the date. Web-based, couple opportunities, training classes. We run them regularly. You're too late for one this week, but a great way to try the software is with training. We have one in January, one in February. Those dates are there. Contact us if you have interest. And then monthly webinars coming up. We have on our other product, ArenaFlow is available on the Altair Partner Alliance. So we have a webinar on that coming up January 28th. And then the next two installments in this application model webinar series. So February 11th, we're going to be talking about the direct reduction of iron and demonstrating that application model. And then in March, we'll have the fourth installment on cement industry applications. And with that, we're going to get to our Q&A. So Shashank, if you're ready, I'm just going to start going through these. There's a number in the chat. If you've not thought of one, or if this discussion triggers one, please continue asking that. And I'll just get started here. Okay, so the first one is how do I change? Can I change the fluid and particles in the application model?
No, that's actually a great question, and that's actually, you know, points right to this intention of providing these application models. We absolutely want you to do that. You know, we have picked up one set of conditions down here. We have defined one PST, you know, and one field properties, but take this model and change it to what you need to be, and that can be absolutely done. As I was showing to the GUI, you can input your own PSD, you can change the fluid properties as you want to, and that's precisely what we hope this model will act as a starting point for you to do.
Okay, and then I'm going to do some of these out of order, but I'm trying to clump ones that have commonality. So can you define a new proppant, higher density, lower density, and so forth?
Absolutely. I mean, so in this particular case, you know, again, what we have also done and studied is you can actually inject two different proppant types here. So in most of the cases, we have only injected 40 by 70, but you can also define another species type. For example, that could be your 100 mesh, and then you can actually inject both of these simultaneously, or you can stage them and inject them within the Barracuda simulation. So that is actually something perfectly possible to do.
Thank you. Do you think you can accurately model segregation deposition of a mixture of proppant / particle sizes and show their location in the fracture?
So obviously, you know, the mixing and the segregation, the settlement behavior, that, you know, again, it depends on you know, the fluid type there, you know, viscosity of the fluid, the inertial forces it's experiencing, and on the top of it, the gravity. But that's the whole idea behind accounting for the full PSD, is that these particles actually, based on their size, experience those forces differently. Now, in some of these examples that I've run down here, you know, this is a well-mixed mixture. But again, if you are running even, you know, larger fractures, you know, where gravity is even more significant, because we have seen fractures of heights, you know, more than what we have done down here. This could be 50 feet, 100 feet height. They actually start seeing that influence more significantly, and that's what we are hoping to capture, you know, when we define this full PSD.
Great, and this one looks related. Can you mix different proppant materials? So in your first answer, or in your prior answer, you mentioned the particle size distribution, but what about materials that could be affecting things like density?
Absolutely. I mean, you know, to Barracuda, each one of these is a particle species. Now you can define any number of particle species essentially, and these species can vary either in size, or they can actually vary in the properties itself. So for example, density can be different, and that can be absolutely done.
Okay, I have two questions here that might be getting at the same thing from different askers. So one says, does the model account for different shaped particles? And another says, is the proppant's sphericity important?
Spot on, and I think they're both related. The way we count for the particle shape is through that specification of the sphericity, and then using a drag model which is more appropriate for non-spherical particles. You know, that's how you would account for that.
Okay. How to model pumping schedule?
Oh, that's actually a great question. Again, that is something that we've also extensively done. The inputs into Barracuda are not just constant numbers. So remember how I was showing that flow rate setup down there? You can either specify a single constant value, or I can actually also specify a time series there essentially. So I can have flow rates, changing as step functions. I could pump in for the first 10 minutes at 30 barrels per minute using my 4070 mesh. I could do the next 10 minutes, pumping at 45 barrels per minute using a different sand size. So all of those combinations are perfectly possible to do, and we do them quite a bit actively when we study these cases.
All right, thank you. Looks like there's about 3 questions left. We still have time, so if you have other questions, please get them in there. The next one is, this is a comment. It came in when you were showing the fracture widths, and maybe some of that post-processing that you did on it. It says frac widths of 1 inch are unrealistic, likely no more than a 1/4 inch near the wellbore. Can you comment on that? Was that, and I wasn't really clear, were you showing it on the demonstration of the commercial scale when you did that post-processing, or was that on the lab scale?
No, this is on the commercial scale, and that's actually spot on. I think these geometries, we again took from a certain literature where that's how this was specified. But that is spot on. Actually, we can actually define fractures which are more thin than 1 inch. I think for this particular study, we wanted to stick to what's already out there published in terms of the geometries and some of these dimensions, and that's what we went with here.
Great, thanks for the comment. What about angled fractures and different shapes? And I think this talks about the shape of the fracture, maybe not, what if you want to model not a rectangle, for example?
Yeah, I mean, that's also perfectly doable. Like again, just like any other CFD model, you can't really have, generally these fractures, in the formation are pretty rough. So that is something that, typically, that roughness grain may or may not be possible to capture down here, but we can absolutely have different shapes. Now, these fractures don't have to be vertical as well. They can be inclined. We could also have branching fractures, essentially. All of those domains can be defined in your CAD model. And once we bring them into Barracuda, we should be able to grid them and solve them.
Okay. Can I try the model if I don't have Barracuda? This is more of a commercial question, so I'll answer that. The answer is yes, certainly. Typically, the best way to do that is in a training class. We do have the web-based trainings, and we can combine. We do provide licensing for the training week and perhaps even shortly thereafter. We want you to know if this is right for you. So contact us and we'll find the right arrangement for you. This is a follow-up to something you said earlier. It says, so when you mix proppants, or say pump 100 mesh first at one rate and then 40/70 at the second rate, can you show where each of the proppants are located after the pumping is completed?
Absolutely. That is actually a post-processing variable available to us where you can color each one of those species with a different color. Right, so I could color my 40/70 mesh with blue. I could do the 100 mesh with red, and they will absolutely show you where these particles are settling down. In fact, I can start blocking regions where I want to focus on, or I can block one particular size from being visualized, and I can only visualize it at one set. So all of these are actually pretty commonly used post-processing tricks with Barracuda, and the same can be applied for this particular problem as well.
Yeah, I think that would be probably pretty important to understand what, how the different materials or proppants and flow rates all interact. One more question here. What computer hardware is needed for proppant simulations?
At least the application model we have on our website, you can just run. You don't need a GPU to run that. You can locally run that on your laptop. But for some of these multi-fractures I was showing, for something like that, we would strongly recommend using a GPU. Again, purely in terms of computational speed, Barracuda can absolutely be run on a single CPU or multiple CPUs. In terms of the grid counts and so on. Those are all something that can very easily be handled. but the turnaround times are usually greater if you use CPUs. For this particular example, as I was showing, to run that 20 minutes pumping time on one GPU card, it took me about 16 to 17 hours to do that. So for those speed ups, I would strongly encourage to use GPUs.
Okay, and that is the questions that have come in. So with that, Shashank, thank you for putting this together and presenting today. I certainly want to thank everybody for joining. This will be posted to our website probably in the next 24 hours, hopefully less. And so if you want to share it with somebody else, please do. And with that, this concludes today's webinar. Thank you all.